So I will be speaking about resonating valence bonds and its quantum information perspective. So this is a bit of a change from what I had planned to say. So I wanted to speak about this is a part of that. So there for like the past 10 years or so, there is a subject growing, the interface of quantum information theory and condensed matter physics, ultra-cold gases on the other hand. This is sort of a bridge between these two sciences that is being built. And there are a lot of interesting applications here. And instead of giving you a broad overview of the entire thing, I will now focus on a particular aspect of it, which is being worked in our group in HRI. And you will see. So it's about something that is called resonating valence bond. I will tell you what resonating valence bonds are, what is the importance of that, those states, and how they can be handled by using quantum information techniques. So it's sort of a brief outline of the talk. I will begin by telling you about the motivation and then telling you about what these states are. I will define them. I mean, resonating valence bond states, there is a common joke that number of papers on RBB states is equal to the number of definitions of RBBs. So it's better to give a correct definition in which I am working or we are working. So these states are defined on some lattices, and in particular I'll show that if the lattice is isotropic, that it is the same if whether you look in this direction or this direction. In that case, the two-particle entanglement, nearest neighbor two-particle entanglement does not exist, in the sense that is very small. This no should be with an inverted comma, is very small, whereas there is a substantial amount of multipartite entanglement for isotropic lattices. And to find out how much multipartite entanglement or any type of entanglement is there in this, we present a method which I will tell you very briefly, which we call the density matrix recursion method. It is a recursion method to generate RBBs, and they can be used for isotropic lattices and as also for non-isotropic lattices. And I will give a conclusion at the end. So we begin with the motivation. Well, RBBs appeared quite early, and it probably first discussed by Linus Pauling in chemistry. And there are a lot of other uses of it. I will not go into all of them, but I am tempted to discuss about this, very briefly about this, where Anderson and his collaborators claimed that RBBs are important for high TC superconductivity, although later on there has been a lot of debates on that, whether that is true or not. But this particular aspect gave RBBs a lot of light, so to say, advertisement, so to say. And there is a nice review on different aspects of RBBs by Professor Bhaskaran in Chennai in this paper. It's in Indian Journal of Physics. It's also available on archive. And so this is about why they are important. And there are other things which I am not going into. Let me directly go into and tell you that these RBB states have recently been realized in different systems, including in this system of photonic system, Walther, Zeilinger and these people. They have realized RBB states in photonic systems. And there is this group of Bloch where they have realized it in cold atoms. So, I just wanted to stress that RBB states are sort of interesting, and not only that, they can be realized in the labs. So, let me first of all tell then what are these RBBs, at least the definition that I am using. So, whenever I will talk about RBBs, there will be a lattice in which I will speak about. There will be different lattices. One of them, for example, this lattice I will actually not use, is just given in this slide. So it's a triangular lattice. So it's a lattice, you can think of it as an infinite lattice. And so these are triangles, and at every side there is a spin-half particle. Okay, there is one spin-half particle at every side, quantum spin-half particle. And these guys, these are singlets. These are singlet states. So we have already seen singlet states in Professor Panigrahi's talk. Just to be complete, I write them here. I hope you can see it. So it's spin up in some direction, let's say Z, up down minus down up, and at some side. So let's call it 1, 2, 1, 2. So let us, if this is site 1 and this is site 2, this guy is denoted as 1, 2. Note that this is not the same as 2, 1. There is a change in phase. Yes? So, of course, if you just take this state separately, then this and this are the same thing. It's just a phase and you cannot detect it. But we will use it in a superposition, and then this phase will be useful. So, this guy and this guy will be different in our case, and we will call it a directed singlet, or sometimes called a dimer. Okay? There can be many such configurations by which you can cover the whole lattice by singlet. So this is one particular configuration, and any such configuration is called a covering. And there are many such coverings of a given lattice. This is one, and there can be another, and then you can superpose them. And when you superpose, it becomes important in which direction you are taking, because the sign becomes important. And in that case, it becomes, this triangular lattice becomes a bit inconvenient to use in that case, because it is difficult to consider this as something into a bipartite lattice. And let me say what is a bipartite lattice. It is easily defined when you take this type of a cubic lattice. So again, it's the same thing. It is the cube of, is a lattice, of the cube is a lot of cubes and goes to infinity. And at every site, there are spin-half particles, a single spin-half particle at every site, single quantum spin-half particle. And now, I define what is a bipartite lattice. Look at any one spin, for example, this one, this is a green. This is this is colored green, so this is in something called sublattice B, is an element of sublattice B. And every neighbor of that is red. So look, if this side is red, this 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 is red. Yes? All of them are red. And now, and this is true for everyone, all of the greens are surrounded by reds. And vice versa. All of the reds are surrounded by greens. Look at this red. This is green, 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 and there is another green that is coming out that is not shown here. Okay, so and this is what is called a bipartite lattice. And in this case, it is easy to define such RBBs. What you do is, you consider these singlets always from a site in sublattice A to a site in sublattice B, never the other direction. And you do the coverings in this way, and you take superpositions of such coverings. Okay? And by taking different, and all these superpositions gives you different RBBs, and they have different names, I'll tell you. So for example, you take a singlet from this to this, and then this one is from this to this, Now this being green, it could have been covered by, it could by a singlet from here, or a singlet from here, or from here, or from here. Yes? But never from green to the other. Okay? And by this you can cover, and there is a large number of, it's exponentially large actually. And you can do the same thing in 2 dimensions, yes? So this is again is a square lattice. All the red sides are surrounded by greens. All the green sides are surrounded by reds. Like that, okay? So, and this, so you take all such coverings, multiply them with some function, call it a covering function, and you take a superposition of them. This is called an RBB. This of course is a class of, is a large number of RBBs, because if you change the H, you get different RBBs. And depending on what this H is, you get, there are names given to RBBs. And for example, well, I just wanted to write Ij is up, down, minus down, up. And so this is again the same thing. And yes, so what we do is we assume that first of all, here we are taking an isotropic lattice. It is not a ladder, it's the same in both directions. Whatever, I mean, this direction doesn't exist, but the directions that exist, in those 2 directions, it is infinite or periodic. And H is assumed to be isotropic over the lattice. So, if this bond comes the same number of times as this bond, yes, is isotropic over the lattice directions. This may not be true, but in our case we assume that. And of course you can have a large number of RBBs, as I said, by changing the H. We just give you 2 extreme examples. If you take the coverings of only nearest neighbor dimers, that is, if you do not, in principle, I have always been telling you, showing you singlets from here to here, but you could have taken a singlet from here to there. If you don't do that, if you only take coverings of nearest neighbor dimers, in that case, so for example, this is one cover, here is another, and you take all such coverings, that we call an RBB liquid. It is not a standard notation, but we use it just for, we didn't have a name, so we gave this title. You can have the other extreme example, where this H is a constant over all coverings. Okay, you have arbitrary coverings. Of course, again, respecting this sublattice rule that you should always have from red to green, but you can go from this green, this red to this green. Okay, so H is a constant, and that we call an RBB gas. Again, this is not a standard name, standard nomenclature. Okay. So this was what RBB states are, and now we show this, try to see how this is of course a huge state, and it is entangled over in many ways, and we show that if you take that state and you take nearest neighbor sites, that state is almost not entangled. It's very little amount of entanglement. However, the entire state has a lot of multi-party entanglement. So it is somehow, the regional entanglement is 0, but the global entanglement is very large. So this is what we will try to show. So this is, so the first part, I will show that in any 2 or higher dimensional isotropic RBB state, the bipartite entanglement is insignificant. This was shown in this paper, that's quite a few years back. And I will not give you the entire proof, but I will give you a sort of an idea of the proof. When we use tools from quantum information, this monogamy of entanglement and quantum telecloning. So you have already heard from Arun about what is monogamy of entanglement. By the way, I mean, just to be politically correct, I mean, neither Arun nor I were involved in coming to this name. this was given by other people, so we are not the people to blame if you don't like the word. So let me, just like Arun, I will just quickly recapitulate what is monogamy of entanglement and how it can be used in our case. So we have a state of n particles. So in particular, that can be a state of n sides of a lattice. And what we do, we consider these two, so it's a state rho n of n particles. So this rho n means is not of only n, okay, it's 1, 2 up to n. There's a n particles here. It's a mixed state, can be pure, of this entire thing. And now you trace out everything except these two guys. And the entanglement of that I denote by tau 1, 2. Some measure of entanglement. Then I trace out everything else except 1 and 3. I keep the 1 unchanged. Okay, so this is 1, 2, this is 1, 3. And you have 1, 4, and so on up to 1n. So you take 1 with everybody. The sum of all of them have to be bounded by this guy. This is not true for all measures, as Arun mentioned, but it is true for something that is called the tangle. I will not prove that, but I will just assume it. So this is the pictorial demonstration. So if you take the sum of all of these guys, that's less equal to the entanglement in this partition of 1 versus the rest. Okay? And why is it called monogamy? Because this guy is bounded above by 1. This is independently known. Now look at the extreme left and the extreme right. Suppose one of them becomes very high. Then because of this bound, all the others have to be 0. So this implies that if one is strongly correlated with someone, it cannot have large correlations with the others. This was introduced in this paper. There are actually other papers before this that also mention it a little, including the cryptography paper that Professor Arthur Eckert was discussing today. But it was really written in this form in this paper, and later on it was generalized by these people. So this is one thing that we use, and so the way we use it is suppose you have a bipartite lattice, square lattice, and then I want to find out how much entanglement is here. I want to find an estimate of this entanglement. But now, this entanglement by symmetry, because of this isotropy, is the same as this. Is the same as this. Is the same as this. So, I have, so my now n is 4. So I have 4 terms here. All of them are the same, and that is bounded above by 1. It's actually bounded above by this, but that is very hard to calculate in this case. So I should ideally calculate this, but that I couldn't calculate. So what we do is, what we find is that there are 4 guys in a square lattice, and for the RBB liquid, the tangle, this is this measure, 1, 2, that can be anywhere but nearest neighbors, is less equal to 1. So this shows me that the tangle is bounded above by 1/4. So this gives me a bound on the entanglement that is not very good, but it's something, because the tangle actually can vary between 0 and 1. So I have at least removed the 3/4 of the portion. But it can be made stronger by using other arguments. And that is what is something called quantum telecloning, and I will not discuss it here, but I just wanted to tell you that it is sort of a mixture of what is known as quantum teleportation and quantum cloning. So in quantum teleportation, you want to send a particle from here to there, and in quantum cloning, you want to prepare copies of a given state. So you have a given state and you want to prepare many copies. And this quantum cloning is known to be not possible. So this was shown by many people, including Wouters and Zurek. And what you do, you prepare approximate copies of that. Quantum cloning combines these two concepts. So it tries to send a copy through a shared state to many people. So it's like this. So there is a guy that is sharing a state with these three guys. It can be many guys, but we need three. So that is why I am giving you three. And this is the input, just like in the teleportation thing. And I do some measurement, and I want to prepare exact copies of that input here. That is not possible, but I prepare approximate copies of them. And these people have shown how close this thing can be to this input. And exactly by using this type of things, I can show that in the case of the RVB liquid, the entanglement is bounded by this small number. So from 0.25 you can come to this much. So this is not the same measure, this is tangle here, so this is a bad notation. So this is tangle, which is the function of entanglement of formation. It is a monotonic function of entanglement of formation, but they are related. And this NN means nearest neighbor. So, and this is done for the RVB liquid on a square lattice. So I take a square lattice, I take the RVB liquid there, and I use this no cloning constraint, no telecloning concept, and I find that this is the bound on the entanglement of formation of any two nearest pairs. So when I was all the while saying that there is no bipartite entanglement, this is what I was meaning. Okay, it's not zero, but it has an upper bound. I don't know whether it is zero, so I don't have any better value. This is the best value that I have. Okay, so I must also add that although we are talking always about entanglement, but typically in condensed matter theory, people are interested in correlations, and the method also, this same techniques can be used to provide bounds on 2-point correlation functions also. So suppose XX correlations or ZZ correlations. So what we have got until now is that if I take an RVB state, resonating valence bond state, so this I must also mention that I showed you for square lattices, but you can show it for cubic lattices or honeycomb lattices in 2D and many other lattices, but has to be in 2D or in 3D. In that case, not in 1D. So in this case, we have shown that there is no bipartite entanglement if the lattice is isotropic. So again, this no is with the inverted comma, it means very small. So of course there are two immediate questions. Yes, what about non-isotropic lattices? Suppose they have a ladder of spins. This is a non-isotropic lattice. Do you have no bipartite entanglement there? And the other question is, what about multi-party entanglement? Okay, you have an RVB on a square which has very little bipartite entanglement, but do you have multi-party entanglement there? So we will take these questions one by one. So one of the questions was taken by two other members of the group. This is Himadri Dhar and Aditi Sen. They published this paper. At that time, both of them were in. This guy is still in JNU. At that time, she was also in JNU, and they published this paper, where they showed that, and their paper was actually one picture was selected on the cover of the journal, and they showed the following, that very unlike to the situation that we had on the square lattice, the ladder, so this is again a ladder of spins, so it goes to infinity or it's periodic on this side. And it's again a bipartite lattice. You see, so this is a green, it is always surrounded by reds. This is a red, it is surrounded by greens. What they showed is that the RBB ladder is approximate, is not exactly this, but is almost very close to this. So you have a singlet here, singlet here. So this means it is directed from the red to the green, just like I wrote here. And this. So this entanglement, this is a singlet. So singlet means its bipartite entanglement is maximal. So it has the highest entanglement that is possible for a two-party state to have. Whereas in the other case, remember that in the isotropic case, well, it shouldn't write isotropic for the square. For the square, we had that entanglement of formation is less than 0.023. But in the ladder, you have entanglement of formation equal to maximal. But the maximal is here. Here it is 0. So it's 0 is the two extremes. Again, these numbers are not exact, okay? I mean, these are approximately 0 and approximately 1. So what I want to stress here is what I wrote already in the previous case, is that previous page, is that the geometry of the lattice has a significant impact on the entanglement content of the RBB on that lattice. Okay, so we had two questions. One question we sort of answered, that bipartite entanglement can be yes and no, in the sense it can be maximal or 0, depending on which direction you are. There are two types of, unlike isotropic lattices, there are different types of bipartite entanglement. For the ladder, there are two types of bipartite entanglement, and one is maximal, one is close to maximal, another is close to 0. So now the next question, what about multiparty entanglement? In these cases, I will mainly focus on the on the isotropic case. So here I must tell you about what is entanglement, because for bipartite entanglement there is essentially, at least conceptually, there is a single measure of entanglement. There can be many ways to measure it, but essentially it's the same concept, especially for pure states. But for multiparty states, there are many types of entanglement. For example, if there are 4 particles, you can have a singlet here and a singlet here. So this state, is it entangled or not? Of course, it depends on what is your definition. So what we will do, we will define something called the genuine multiparty entanglement, where we will call that this entanglement, the multiparty entanglement of the, let us call it EM, this is 0. We don't want to call it entangled. Or, if I have a state like this, so there are many people, including Arun, they were defining GHZ state. Suppose this is a GHZ state, which is up, 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 plus down, 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 1 over root 2. And suppose this is just the up state. Okay, so the GHZ is this. So this state, well, this part is of course entangled, but here it is separable. So it has some amount of entanglement. You cannot create this state, neither this nor this, by keeping all the particles far apart. But also we want to call this as 0 because there is at least one partition where the entanglement is 0. So we want to define something that is called the genuine multiparty entanglement. So, and it's So this definition is valid only for pure states. For mixed states, one has to change this definition. But we will be working only with pure states. So a multiparty pure state is said to be genuinely multiparty entangled if it is entangled across every bipartition. Whatever bipartition you do, it has to be entangled across every partition. And now I also want to just stress another point, is that if you have some particles and some more particles here, and so this is 1, 2, 3, and so on up to n minus 1, and this is one partition. And the entire thing is in a pure state. And then, if I want to check whether it is entangled across this partition, that is, I want to check whether it is entangled across 1, 2, 3, 4 versus rest, then it is enough to see whether the local density matrix of this part is mixed. That is enough. So if I take this state, I trace out everything except 1, 2, 3, 4. Okay, so I am denoting in bar. I have traced out everything except 1, 2, 3, 4. I get a state of, some state can be pure, can be mixed. It is known that if this guy is pure, this implies that this state is separable across that partition. If this guy is mixed, it is one-to-one correspondence. This implies that partition is entangled. Okay? Actually, a very good measure of the entanglement in this partition is the von Neumann entropy of the local density matrix of this state. Okay? So, if I can show that the von Neumann entropy of this state is 0, that is for the pure state, then that partition has no entanglement. If the von Neumann entropy of this guy is not 0, that is greater than 0, then it is entangled. Fine, this I will use. So now, I will show, and this was actually a very recent paper by Himadri, Aditi and me, where we show, it was, a part of that was already there in the previous paper, but here we show it in general, that if you have an isotropic lattice, then the multiparty entanglement is non-zero, that it has a genuine multiparty entanglement. So what I do is, I consider an odd is to rest bipartite partition. A partition like this, where the number of particles here is odd. There are odd number of, so this is an even is to rest partition. I am not considering that. I am considering a partition where on one side there are an odd number of particles. Finite, of course, and odd. I will do the infinite case later. So I will trace out everything except those odd particles. And now, so these are examples. So so that odd can be 1 particle, can be 3 particles, and that 3 particles can be like this or like this. There can be 5 particles and many others. And now I use an interesting fact. You know that the singlet state is rotationally invariant. And now this RVD state is created out of superpositions of these rotationally invariant states. And one can show that if you have, it's just a simple addition rule of angular momentum, that if you have an odd number of spin-off particles, then there is no quantum pure state of those particles. You cannot have a pure state of an odd number of spin-off particles. And so, this state cannot be pure. If it is 1, if it is 3, this 3 or that 3, this 5 or any other 5 or 7, 29. This thing cannot be pure. And thereby, by this, it implies that any odd is to rest partition is an entangled state. So it has, this state has entanglement across every odd is to remaining partition. Okay? So we are remaining with the even is to rest. Let us go to the even is to rest. And in this case we do by an example, you can do with other cases also. Let us consider 2 is to rest. As yet we don't know whether 2 is to rest is separable or not. So we take this 2. Next consider this 2. Now this state by isotropy is the same as this state. And let us assume that this guy is pure. Therefore, this guy must also be pure, because it's the same state. Now consider, look at this state. You can show, I will not go into the proof, there is something called strong subadditivity of von Neumann entropy. By using this, you can show that if this thing is pure and this thing is pure, then the common site must be a pure state also. But this is a contradiction, because we have proved that the odd is to rest partition is entangled. We have just before we proved that single site is a mixed state. It's actually half I, because for a spin-off particle that's the only option that you can have for the RBB. So this is a contradiction which implies that the 2 is to rest partition is also entangled. Because what did we start with? We started with the fact that this green boundary consists of a pure state. We assumed that. That implied that this red boundary is pure, and that through strong subadditivity implied that this blue thing, if you can see this blue, this single side, this is a pure state. That implies, and that is a contradiction because that cannot be possible, this is a mixed state, we know it from the odd is to rest case. So, the first assumption must be wrong. So we must have that these 2 particles are in a mixed state. Which again, we come back here and we say that because it is mixed, it must be entangled. So this shows, so odd and even are both non-zero, but that is not the end, because one can have a partition like this. So this shows that all finite is to rest partitions are entangled, but one can have infinite partitions like this. What about this partition? Whether this is entangled, but that also one can show. So until now we have shown that it is genuinely multiparty entangled, whatever is the system size, but it can well happen that it is entangled for every n, but as n grows, it grazes to 0. It can asymptotically graze to 0, whether that is true or not, whether this genuine multiparty entanglement survives in the limit of infinite lattices. And this is what we will do. We will show that we will explicitly show it for the square lattice on 2D, that even in the limit of infinite size, we will do it by finite size scaling, that there is a substantial amount of entanglement, genuine multiparty entanglement, even in the limit of infinite system size. So that brings us to what we call the density matrix recursion method, and I will try to just give a glimpse of it. So just to motivate why we need a separate method to calculate the genuine multiparty entanglement, let me say that consider this ladder of spins. It's a bipartite lattice, and if you want to cover it by singlets, there are 5 terms in that superposition. There are 5 coverings here. And now to find the entanglement, you have to open up this superposition. You have to write it in some basis, suppose the computational basis, and there are 16 terms in each of them. So the total number of terms will be 80. Now suppose there are 5 rungs on that ladder, and there will be 256, and it grows very quickly. With 6, it's like that. So unless we have a systematic method to handle, systematic way to handle such lattices, it is not possible to do it by brute force. This was for ladders. So this is what I was telling. So this is, I was telling it for non-periodic boundary conditions. Typically we are interested in the periodic boundary condition. In that case the coverings increase and it's even larger and it's even difficult. The same thing happens for isotropic case. If you have a square lattice, I mean it's actually worse because there is periodicity in that direction also. So it will be very good if we can have sort of a method, systematic method to handle such states. And one such was given by this paper, and there are a few other papers who give a recursion techniques to generate RVB states. So the idea is like this, which we generalize because in this paper what they do and in the other papers what they do, they give a recursion method, but that method can only be used to calculate energies and correlation functions. You cannot calculate multi-particle terms, multi-particle quantities. So by using our method we can calculate multi-particle quantities also. So the general idea is like this. So you take a basic block. So we are considering in this case a ladder of spins. This DMRM that we call density matrix recursion method, this works for ladders as well as in 2 dimension, and it works for also ladders of so this is a ladder of 2 legs, but it can also work for ladder of 3 legs or 4 legs and so on. But this I discuss it for the 2-leg ladder. So suppose I have a basic block. So this 2 denotes an RVB on this. So this is, so remember we always have from red to the other, or I don't remember, I think it was from red to the other, and this was supposed to be green, sorry. So this is like a, suppose this reds at the A, so it's a singlet like this, and then and like this, or a singlet like this, yes? So it's either like this or like this. These 2 singlets, and you superpose them. So this state denotes that denoted by a square. And then suppose I now want to add another block and try to find out what the state of that is. So what I can do is that I can have this covering. So I have some covering here or a superposition of coverings and I add this cover. But there is another term that is left out, that is this. I can have a covering like this. And for the non-periodic case, you can show that that is all. There is no more that is needed. So, a 4 rungs, so I am calling these as the legs and these as the rungs of the ladder. So a 4-rung 2-leg ladder, so this 4 means rung, can be written by using a 3-rung ladder and a 2-rung ladder. And you can generalize it. But before generalizing, I must also say that for the periodic case, you have this additional term. You have a 2-rung ladder here, term here, and this term. So, the recursion relation for the 4 periodic looks like this. But it does not grow. So, you can show that for n plus 2, you need only n plus 1 and n. You don't need anything else. And this is what we did in these 2 papers. And you can use that technique to calculate bipartite as well as multiparty properties of large spin systems. So I will sort of end here quickly. It can be generalized to multi-legged ladders, and essentially for the odd leg and the even leg, the formulas look a bit different. But I just wanted to stress here that this, look at this. So this is n plus 2 periodic. This involves n plus 2 non-periodic and n non-periodic. And this n plus 2 non-periodic involves n non-periodic and n plus 1 non-periodic. So for n plus 2, you need only this n and n plus 1, that's all. So if you can calculate explicitly the properties of small ladders, so if you have, let's say, a 5-legged ladder, and you calculate its properties for two or three rungs, then you can generate it for arbitrary size. And the same holds for odd-legged ladders, let's say 3 legs or 5 legs. So, and importantly, these recursion relations can be written down for the local density matrices of arbitrary number of sites. So not only the whole state, but you can take local density matrices. Let's say if you have a 3-leg, 25-rung state, but you want two site states. Even that you can do it by using this recursion relation. So it was again sort of an advertisement of what can be done. So now let us apply, because we wanted it to find the value of the genuine multiparty entanglement in a large state. Let us use it. And we use first in this thing that is known already in condensed matter physics, that even-legged ladders, which is sort of surprising, are known, well, are rather predicted, not actually known. There are some approximate calculations that show that even-legged ladders and odd-legged ladders have different properties. In particular, even-legged ladders are believed to be potentially relevant for high T-cell superconductivity, whereas the others are not. And they have some different properties in terms of the gap, if you consider Heisenberg Hamiltonians. So we try to see whether the genuine multiparty entanglement, and so I defined what is genuine multiparty entanglement. This is a measure of that genuine multiparty entanglement. So this measure will give 0 value for singlet or for GHZ and something, but if you have a GHZ of 4 parties, then the 4-party GGM of that state is non-zero, and so on. And I'm not going into the details of that measure, but what we saw is that for the 2-legged ladder and the 4-legged ladder, this is the feature. So this is the number of rungs. So here, this 18 means there are 18 rungs, and so here there are 4 legs. So the total system size is 18 multiplied by 4. And whereas here it is 18 multiplied by 2. And what we see by using this DMRM, that the genuine multiparty entanglement comes down and converges to a value. So these are even legs. Consider the odd legs, it happens the opposite. It comes up and converges to some value. And so what we claim is that we have a complementary scaling of genuine multi-site entanglement in odd and even-legged ladders. So we have that this measure GGM can distinguish odd from even-legged ladders. And the final question is, what is the entanglement of the 2D square lattice? And it's in this paper, and this is the value. So this is the total system size. So here, so I think we went until 56 or something. And this is again the same measure. And as you see that it oscillates and converges to a value. And we use this same technique to find these values. And we have done finite size scaling. What we see is that at infinity, the projected value of this GGM is this. And it goes to this value with this scaling parameter. And this is the scaling formula. So with that I come to my conclusion. So I guess I have been trying to tell you that RBBs are interesting and are realizable in labs. And isotropic RBBs have little or no bipartite entanglement, but significant genuine multi-site entanglement. The situation can be completely opposite in non-isotropic ones, like ladders. And this technique, DMRM, density matrix recursion method, is an useful analytical method for both cases. In particular, can be evaluated, can be used to evaluate genuine multiparty entanglement in both cases, both meaning in non-isotropic as well as in isotropic cases. Okay, and so this is, Arun has already showed you our group, and this is the bigger group. Arun is not there, but you can see him here, and these are the others fighting among each other. And this is the guy also who is not, this is Himadri, whose work was there in all the papers that I showed except the first one. And thank you.
Do you have any questions for Professor Sen?
Sir, have you found any application towards to find the lattice defects?
Pardon?
Lattice defects.
No. So this is I think the next work that we are trying to do, because
so
you are right that
precisely, I think that if there is a gap in one of the sides, that still one should be able to find the boundary conditions and calculate.
Exactly. But the calculation becomes very difficult. But we are very much interested in, because the superconductivity thing appears only when, it may not appear at all, but the belief is that it may appear only in the case when there are these holes. But yeah, we have not done that mathematics. We are trying to do that currently.